Now we already discussed what is the COP of a reversed Carnot cycle in the vapor compression refrigeration system. Now we will discuss that how the COP of the refrigeration system will vary and what are the effects of the change in the temperature of the condenser or the temperature of the evaporator. Now if I write again, if we see that we already solved for this, that COP of a reversed Carnot cycle comes out to be, what is that? T lower upon T higher minus T lower, that is TE upon TC minus, this is TC minus TE. TC is the temperature of the condenser and TE is the temperature of this evaporator or the you can say storage device. Now let us say that the COP of a reversed Carnot cycle is only a function of temperature of the evaporator and temperature of the condenser. It is only depending upon the temperature limits between which this cycle is working. It is not depending upon the working fluid, which refrigerant is flowing through this cycle. It is not a function of that refrigerant. It is only the function of this temperature limits. So we can say that if you increase the temperature of the evaporator or if you change the temperature of the evaporator and the temperature of the condenser, the COP of the reverse Carnot cycle will vary. Now if we talk about that WCE is the work consumed by this compressor, right? We can say that the work consumed by the compressor is WC, heat rejected in the condenser is QR, work done by this turbine is WT, and heat supplied or heat absorbed by this evaporator in this evaporator is QS, right? And we already know that one second. We already know that from the first law of thermodynamics that for a closed cycle the net work will be equal to the net heat supply, or you can say that WC minus WT will be equal to heat rejected minus heat supply. This you know, right? And this is equal to W net work done. And for the reversible cycle, you very well aware that the heat will be equal to TDS. You know that this is for a reversible cycle or reversible process. You can say this is for a reversible process from the second law of thermodynamics, from the entropy that formula we get this dQ is equal to TDS. It means that dQ is this, TDS is the area under temperature entropy diagram when it is projected on the entropy axis. When this is projected on the entropy axis, the area will give you your net that heat transfer in that process. So if I say that if I extend it, let us say like this, so we can say that the heat rejection will be the area under this 2-3 curve. Under this 2-3 curve, when it is projected on the entropy axis, this is the entropy axis. So when it is projected on the entropy axis, the area under this 2-3 curve, this complete area is the heat supply, or sorry, heat rejected, right? If I draw this for your better understanding, let us say, if we again draw the TS diagram for just to make you clear, right? So this is the cycle, reversed Carnot cycle. Let us make this, right? Okay, a rough diagram will make so that you will be clear, you will be more clear about the areas. So if I project it like this, so this area, this complete area this complete area is giving us the heat supply. This complete area is giving us the heat rejected. This will give you the heat rejected. What is the heat rejected in this condenser, in this process? And if we talk about the heat supply or heat absorbed during the evaporation or during this evaporation process, in this process, then the area under this curve, under this 4 to 1 curve, this area is this black shaded area, this area is the heat supply. So if we can say, if this is this complete area is the heat rejected and this area is the heat supply, so this net area, right, this net area, this area will give you the net heat supply, that is QS minus QR, or you can say QR minus QS, because heat rejection is more than the heat supply or heat absorbed, right? So this is QR minus QS, right? And this is equal to net work done. From here you can write this is equal to net work done. So if I draw here, then this shaded area, this area enclosed by this curve, this area is the net work. This is basic thermodynamics. If your thermodynamics concepts are good, then you will be better understand this. This is the net work done, and this area, this black shaded area, this is the refrigeration effect, or you can say this is the heat supply. This is the refrigeration effect. So if I say that, we will rub this is just for your understanding, so that you will not be confused that why we take this area under this curve or under this complete cycle is the net work done. So we'll see now. Now let us say that, because we know that the COP is equal to refrigeration effect upon your net work done. Refrigeration effect upon net work done. This is the COP. So if I say that, let us say this is point A, this is point B. So this will be equal to, what is the refrigeration effect? This is the area of, this is this area B14A, area B14A divided by net work done. Net work done is this area, that is area of this 1, 2, 3, 4. This is the COP of this reversed Carnot cycle on the vapor compression system, right? Now we can say that the COP of a Carnot refrigeration system increases as the evaporation temperature increases. So if I write here that COP will increase if you increase the evaporation temperature while making this, COP will increase by increasing the evaporation temperature by making this condensate temperature constant, or you can say that it will increase by decreasing the condenser temperature. If condenser temperature is decreasing, then the COP of the Carnot cycle will increase, right? Will increase. Now let us see that. First of all, let us say that for a constant evaporation temperature, if we put this evaporation temperature, this temperature constant, if I put this evaporation temperature constant, and we will decrease the condenser temperature. Condensate temperature will decrease, right? This condenser temperature will decrease. This will remain here. This condenser temperature will decrease. If this condenser temperature will decrease, then the area of this curve will decrease, right? If it comes down and it will be here, then the area will be decreased. So we can say that if you decrease the condenser temperature, then W net will decrease. W net will decrease, but this is constant. Evaporation temperature is constant, so the refrigeration effect will be same. Refrigeration effect will be same. So if I write now that the COP of this will be equal to, COP is refrigeration effect upon W net. So by decreasing the condenser temperature, your refrigeration effect will remain same, but this W net will decrease. This W net will decrease, then this COP will increase. Because denominator is decreased, so this COP will increase. So that's why we can say that the COP of a reversed Carnot cycle will increase if you decrease the condenser temperature, if this temperature is decreased. Now, if we make for second case, if we say that for the constant condenser temperature, for the constant condenser temperature, if I make this condenser temperature constant and I increase the evaporator temperature, and we will increase the evaporator temperature, right? This line will increase, this evaporator temperature will increase. Suppose now here is the evaporation temperature. So if this is increased, this will remain constant, Tc is constant, this T is increased. So if this will increase, then we can say that this refrigeration effect will increase, right? Refrigeration effect will increase. Why? Because the area is increased, so the refrigeration effect is increased. So we can say that this refrigeration effect is increased because the area is increased. And this, what is about this W net? If this line will move upward, so the area of this W net is also decreased. So this W net is also it decrease. W net decrease, right? W net decrease. So if I write that COP, that is equal to the refrigeration effect upon net work done. So we can say that if I make this condenser temperature constant and if I increase the evaporator temperature, then the refrigeration effect increased and W net will decrease. So as a result, because both of the factors will make COP more increased, right? They will make this COP increased. So this is the variation of condenser temperature and evaporator temperature on the COP, right? So COP will increase if you increase the evaporator temperature, and it will increase when you decrease the condenser temperature, right? So if I make the graph that how this COP will vary with the condenser temperature and the evaporator temperature, if I make this graph, so let us say on this axis we have COP and on this axis we have temperature, right? On this axis we have temperature. Let us say in this direction evaporator temperature increased, evaporator temperature is increasing. So we can say that the COP will increase if you increase the evaporator temperature. So the lines will go like this, right? Lines will go like this for different condenser temperature. And we can say that in this direction condenser temperature is increased. In this direction condenser temperature increase. If you increase the condenser temperature, then for a given evaporator temperature, if you increase the condenser temperature, then the COP will decrease. If you increase this Tc, then COP will decrease, right? So this is the graph for COP versus temperature based on this result that what we got when we change the evaporator temperature and condenser temperature. Now let us talk about that why this reversed Carnot cycle, or we can say, because we know one thing that the Carnot cycle is the ideal cycle for any heat engine or refrigeration, or you can say heat pump, or for any cycle. Carnot cycle is the ideal cycle because all the processes are your reversible process, and as per the Carnot theorem we know that the COP or the efficiency of any cycle will be maximum between the same temperature limit if we use this Carnot cycle or a reversible cycle. Then what are the practical difficulties with this Carnot cycle? Why we are not using this Carnot cycle? We have to see, right? We will discuss this, that what is the practical limitations of this Carnot cycle, that why there is a need for, you can say, reversed Brayton cycle, or you can say reversed Rankine cycle, why there is a need for it, then we have to discuss it. Now let us discuss what are the practical difficulties with the Carnot refrigeration system. As we know that this is an ideal cycle for any heat engine or the refrigeration, but still we are not using this Carnot cycle because there are some practical difficulties which are associated with this Carnot cycle. That's why we have to use this Brayton cycle or the, you can say, Rankine cycle and so on. The first very easy to understand first difficulty is that no process can be reversible, because reversible process is not feasible in actual. If we talk about in reality, that no process will be reversible. They are always associated with some frictional losses. Some losses will be there. If we talk about isothermal process, then because you know that if you want to achieve an isothermal process, a reversible process, then the temperature gradient or the temperature difference for the heat flow during the isothermal process must be very, very less. It is almost tending to zero. That is practically, if we talk about, then that is not possible, because if we make that process a reversible isothermal process for heat addition or heat exchange rather than, we can say, then that process is very, very slow, right? Because you have to increase the temperature very slowly so that the temperature difference will be almost zero. So in reality, that reversible process is not possible, because some of the frictional losses or some kind of dissipation must be there, right? This is the very easy to understand for practical difficulty with the Carnot cycle. Because in the Carnot cycle, all these four processes are the reversible process, so it is not possible. If we talk about the adiabatic expansion or adiabatic compression, then the turbine, and if we talk about compressor, there must be some losses, because there are some moving parts are there, so some friction must be there. Fluid is flowing, then that fluid must have some viscosity. Some of the head loss must be there, minor losses, major losses. So many losses are associated with it. So reversible process is not physically possible. Now if we talk about particularly or specifically about this vapor compression cycle, then we can say that some of the practical difficulties with this reversed Carnot cycle are: the first difficulty, if we talk about, is with this process 1 to 2, right? This process 1 to 2. This process 1 to 2 is the reversible adiabatic compression, right? If we talk about, if we write here, then we can say that first difficulty, that all the processes are actually irreversible, that is okay. But if we make a process reversible, then also there are some of the practical difficulties associated with this Carnot cycle. The first is that during this process 1 to 2, if we write here, during the process 1 to 2, this process is consisting of liquid and vapor. At this point 1, and the state at this point 1 is the mixture of liquid plus vapor, right? If we talk about, then at point 1, the state is mixture of liquid and vapor. Liquid plus vapor is present, right? And the compressor which is used in this process 1 to 2 will have to compress this liquid plus vapor. This has to compressed, and this compression of liquid plus vapor is known as wet compression. We will discuss this why this is a difficulty, that this compressor which is dealing with both liquid and vapor simultaneously. Here the mixture is liquid plus vapor. So this compressor has to compress this liquid plus vapor mixture, and at the end, at the point 2, we have saturated vapor. At this point 2, we have saturated vapor. So this compression of liquid plus vapor is known as wet compression, and the compressor will face the difficulty under this wet compression. We will discuss it later in your fluid machines when we talk about pump. We can say that a pump, there is a very limited difference between liquid that pump and compressor, right? We will talk about later. But to compress the liquid plus vapor simultaneously is not practically possible, especially with the reciprocating compressor. We can say that this is the problem, this is the first problem, that the wet compression is not practically possible, especially with the reciprocating compressor, and if you want to run that reciprocating compressor at a very high speed. So at a very high speed, because of this presence of this liquid phase, liquid refrigerant, there are some losses associated with the reciprocating compressor. So we can say that some damage to the walls of the reciprocating compressor will be there because of the presence of this liquid. So this is the first practical difficulty with this wet compression. So generally we always try to get the dry compression. Dry compression means when the initial point of compression, this point 1 must be at saturated vapor line, right? If the compressor will do this type of compression, if we talk about, if the initial point is on this saturated vapor line, then this type of compressor, because it is a reversible adiabatic, so this compression is the dry compression when the initial state is at your saturated vapor line, right? This is known as dry compression. This is dry compression. So we generally try to achieve this dry compression in all of the compressors. And if we talk about the vapor compression cycle, or VCRS if you can say, which is based on the reversed Rankine cycle, then we can say that if nothing is given, then always assume that the initial point at the compressor will be at the saturated vapor line. We always want a dry compression, right? This is the first practical difficulty. Second practical difficulty is with this turbine, right? What is the difficulty with this turbine? We can say that we are using a turbine here, right? Here we have turbine. This is a turbine which will give you some work, right? And this turbine is a open system, so we can say that second practical difficulty if we talk about, so the work done by this turbine will be equal to integration of specific volume into dP, change of pressure, specific volume into dP. This we know, right? Open system work. Now, because if you see from here, this initial point of the turbine is the liquid. This is saturated liquid. So if this is the case, then we can say that the specific volume of liquid is very less. The specific volume of liquid is very less, right? This is very less. So if this specific volume of the liquid is very less, then we can say that the turbine work which we get is very less. And if we can say, if there are some of the losses are there, some of the frictional losses are there, then this turbine work will reduce further. So installing a turbine to get a very less work is not practically feasible, is not practically possible, because turbines cost itself is very high. So if you are not getting enough quantity of work which can be compensated by this WC, then there is no use to use this turbine as a adiabatic expander, right? So instead of this, we have some, so because of this practical you can say practical limitations, we modified this Carnot cycle as per our need. We modified it. What we did, instead of this turbine, we use a throttling device to expand. We use a throttling device which is very cheap and very good for the expansion. And instead of this isothermal heat addition and heat rejection process, we are using the, you can say, isobaric heat rejection and heat addition process. Isobaric process to maintain the, if you can see that the reversible isothermal process for heat addition and heat rejection is not practically possible, because that process is very slow process. So instead of that reversible isothermal heat exchanging process, we are replacing it with isobaric, because we can maintain a constant pressure, reversibly constant pressure, while exchanging the heat with the system very easily, rather than maintaining the constant temperature. Maintaining the constant pressure during the heat exchange process is easier than maintaining a constant temperature, because for that you have to see, if we can say that because isothermal heat addition and heat rejection process, that too reversible, is very slow process. So these are the two practical difficulties. Now we can say that this, if you can say that this dry compression we can achieve easily, right? If we talk about how to overcome this type of limitations, this limitation of the dry compression, we can overcome this dry compression, this wet compression limitation, by using two compressors. If you are using two compressors, what you want, let us say here, this is the constant pressure lines, this is PC, that is the constant pressure corresponding to this temperature TC, and let us say this is expander pressure PE, or evaporator pressure, you can say. These are the constant pressure lines. Now if you want to achieve this dry compression, how you can achieve? Let us suppose we will use two compressors like this. Let us say this is TS diagram. This is a vapor dome. We can use two compressors, one which is giving you the reversible adiabatic compression. Suppose, let us say this is your compressor 1, WC1, from point 1 to 2. This is reversible adiabatic compression 1 to 2. Let us say that this pressure is PC. Let us say this pressure is PC, right? So we will compress this refrigerant from point 1 to 2 up to some pressure. Let us say here the pressure is, let us say at point 2, let us say the pressure line is this one. The pressure line is this one. Constant pressure line at this point 2, if you write 2 here, this is the some intermediate pressure line, right? And from this point 2, but because you need at the inlet of the condenser the condition at point 2. Condition at point 2 here is that saturated vapor corresponding to this pressure PC. So to come to this PC, you need this type of compressor. This is second compressor up from point 2 to 3. This pressure corresponding to this is PC. This is PC. So from point 1 to 2, this process 1 to 2 is reversible adiabatic compression. Reversible adiabatic compression from pressure P1 to intermediate. And process 2 to 3 is isothermal at constant temperature. This compression is at constant temperature. So this is reversible isothermal compression. Reversible isothermal compression from pressure P intermediate to condenser pressure. P intermediate to PC. From this pressure to this pressure, we are using second compressor, that is from 2 to 3. And then in the condenser, we have this heat rejection. From 3 to 4, heat rejection. From 4 to 5, we have expansion in the turbine. And then we have heat addition in the storage. This one. So this type of Carnot cycle you can use to overcome this limitation of the wet compression. But now you have to use two compressors. This is WC1 and here it is WC2. You can use it, right? So this type of modification you can do to get the Carnot cycle, right? Now we can say, if you don't want now to install two compressors, and that two different process compressor, one is adiabatic, one is isothermal. Instead of this, we can say that the dry compression, we always want dry compression. Make one thing very clear, we always want in this cycle that the compression process must be dry compression, because wet compression is not practically possible. Right? There are some of the limitations associated with it. We will discuss it in your pumps when we talk about pumps. Now, if you want to achieve this, then suppose in this diagram only, if we say that I want to achieve this dry compression in single compressor, in only one compressor you want to achieve, you don't want to use this second compressor. If I don't want to use this second compressor and only with this first compressor I want to achieve this PC, this is PE, right? This is PE. I want to achieve this. Now that means if I rub this, now that means that the inlet of the condenser is at point 2. The inlet of the condenser is point 2. Now from this point 2 to point 3, if you want to do the heat rejection process, then that must be isobaric. This heat rejection process from 2 to 3, because you don't change this pressure. This PC you cannot change. If you want to achieve this dry compression in the single compressor, that means from PE to PC you want to get from one compressor only. So if I get this, then the second point in the superheated region, the second point is the outlet of the compressor and inlet of the condenser. Now in the condenser you want to reject the heat and you want to come to this point 3, which is corresponds to this temperature Tc. So there is only one process left which you can take, that is this constant pressure heat rejection. You can only take this constant pressure heat rejection. So to get this dry compression in the single compressor, then we can say that you have to replace isothermal heat exchange process with isobaric process. This is the one modification, with isobaric process. right? We want to overcome these two limitations of the Carnot cycle. And so one limitation can be overcome if you use this isobaric heat exchange process, and second we can say that this isentropic expansion, which is not economically possible, rather than you can say, so if you replace, second limitation will be overcome if you replace isentropic expansion with isenthalpic expansion, that is by using throttling device. If you replace this isentropic expansion with isenthalpic constant enthalpy process, then we can overcome this limitation of the WT, right? By implementing these two modification in the Carnot refrigeration system, you will get the reversed Rankine cycle. I hope you will be understand that why there is a need for the reversed Rankine cycle when we have the perfect cycle for this refrigeration system. Because of this limitation, and to overcome this, we replace the isothermal with isobaric and isentropic expansion with the isenthalpic expansion, and by implementing these two modifications, the new cycle which will come is known as Rankine, or you can say reversed Rankine cycle, right? So this leads to the birth of the reversed Rankine cycle. Now in the next discussion, we will discuss about the vapor compression system based on the reversed Rankine cycle by implementing these two modifications.